Right now, somewhere on this planet, a child is dying from drinking water. Not from a lack of water. There is plenty of water. The child is dying because the water available to drink is contaminated, and there is no system in place to clean it. And this happens approximately every 90 seconds. Every 90 seconds, a child under the age of 5 dies from a waterborne illness that clean water would have prevented. Diarrhea, cholera, typhoid, dysentery. Diseases that most people in wealthy countries with functioning municipal water systems have never had to think about seriously. Diseases that feel like historical problems or distant abstractions are killing children in 2024 at a rate that should be considered one of the defining moral crises of our time. And here is the part that makes it genuinely unbearable when you sit with it. The filtration technology that could prevent most of those deaths is not complicated. It does not require electricity. It does not require chemicals or pumps or advanced engineering or significant money. It requires a container, some sand, some gravel, some charcoal, and gravity. Materials that exist everywhere on Earth, in every country, in every climate, accessible to virtually every person regardless of income. The knowledge to build a working water filter has existed for thousands of years, was practiced by ancient civilizations across multiple continents, and can be replicated today for less than $2. And most of the people who need it most do not know how to build it, because in the modern world, clean water became something you buy rather than something you make. And the knowledge of how to make it became unnecessary in wealthy places and invisible in poor ones. This is the story of the gravity water filter, where it came from, how it works, and why one of the most powerful tools for human survival ever developed is sitting in plain sight, waiting to be used. To understand why this matters so much, you need to understand the actual scale of the water crisis. Not the abstract version that appears in development reports, but the lived version that shapes the daily existence of an enormous fraction of humanity. Approximately 2 billion people on Earth currently lack access to safely managed drinking water. Not slightly inconvenient water, not water that tastes a bit off. Water that carries a genuine risk of serious illness or death every time it is consumed. Another 3 billion people lack access to basic hand washing facilities with soap and water at home. These are not numbers from a century ago. These are current figures describing the present reality of roughly half the people alive on this planet today. The consequences are not limited to illness and death, as catastrophic as those are. In communities where safe water is not available from a tap, someone has to go get it. And that someone is almost always a woman or a girl. Studies conducted across sub-Saharan Africa, South Asia, and parts of Latin America consistently find that women and girls spend an average of 6 hours per day collecting water in water-scarce communities. 6 hours every day, not 6 hours per week. 6 hours per day that cannot be spent in school, or earning income, or resting, or doing anything other than walking to a water source, filling a container, and walking back. The water crisis is not just a health crisis, it is an education crisis, an economic crisis, and a gender inequality crisis, all concentrated in the same problem. And a $2 gravity filter does not solve all of that, but it solves enough of it to change lives. Before we talk about building one, we need to go back to the beginning of this idea, because the history of water filtration is one of the oldest continuous threads in the history of human civilization, and understanding where this knowledge came from makes it impossible to dismiss it as primitive or insufficient. The oldest known written instructions for improving water quality come from ancient India. The Sushruta Samhita, a Sanskrit medical text dating back approximately 2,500 years, describes methods for purifying water that include boiling, filtering through sand and gravel, and exposure to sunlight. These were not folk remedies recorded by accident. They were systematic medical recommendations made by physicians who had observed over generations of practice what worked and what did not. The text understood that water clarity was connected to health outcomes in a way that would not be formally confirmed by germ theory for another 2,000 years. Ancient Egypt offers similar evidence. Archaeological records and written sources describe the use of clay jars, cloth filtration, and natural materials to improve water before consumption. In ancient Greece, Hippocrates, the physician whose name we still invoke in the oath that doctors take, recommended that water be filtered through cloth before drinking. He designed what some historians describe as the first portable water filter, a cloth bag through which water was passed to remove sediment and particles. The ancient Romans, who built some of the most sophisticated water infrastructure the ancient world ever produced, used settling tanks, cloth screens, and gravel filtration as part of their aqueduct systems. They understood empirically that water passing through layers of natural material emerged cleaner than water that had not been filtered, even without understanding the biological mechanisms that explained why. Across cultures and centuries, the same discovery kept emerging independently. Water filtered through layers of earth comes out cleaner. It was not a coincidence, it was observation. People watched water seep through soil and emerge as springs, and they noticed that the spring water was clearer and tasted better than the surface water it came from. They replicated that process deliberately, first crudely and then with increasing sophistication, and they passed the knowledge forward. The specific materials and configurations varied across cultures and environments, but the underlying principle was universal. Layers of natural material, arranged in the right order with water moving through them slowly under the force of gravity, produce cleaner water than the water that entered. By the early 19th century, this empirical knowledge was being formalized into engineering. In 1804, a Scottish engineer named John Gibb installed the first municipal slow sand filtration system in Paisley, Scotland, providing filtered water to the town. Within decades, slow sand filtration had spread to major European cities. By the 1850s, London was using large-scale sand filtration to treat the Thames water that supplied the city. The timing of that adoption is worth noting because it coincided with one of the most famous episodes in the history of public health. In 1854, a physician named John Snow traced a cholera outbreak in London's Soho neighborhood to a contaminated water pump on Broad Street. His investigation, which mapped the cases of illness geographically and identified the water source as the common factor, is often described as the founding moment of epidemiology, the science of how diseases spread through populations. But what is equally significant is what Snow's work confirmed about the relationship between water contamination and disease, at a time when germ theory had not yet been fully established. People were getting sick and dying from their water, and filtering that water reduced the illness. The science of why filtration worked came later, after Louis Pasteur and Robert Koch established that specific microorganisms caused specific diseases in the 1860s and 1870s. Once science understood that bacteria and other pathogens were responsible for waterborne illness, the mechanism by which filtration reduced that illness became explicable rather than merely observed. Sand and gravel physically trap particles, including microbial cells attached to those particles. Slow passage through fine sand creates conditions where biological activity in the filter itself degrades organic material. Charcoal adsorbs chemical contaminants and organic compounds that affect taste and safety. In time, the slow movement of water through multiple layers allows all of these processes to operate more thoroughly than fast filtration ever could. The science caught up with the practice and confirmed what observation had already established across thousands of years of human experience. Now, let us get precise about the physics and chemistry of what is happening inside a gravity filter, because understanding the mechanism changes how you think about building one and operating one. When water enters the top of a layered filter and begins to move downward, it is subject to gravity in the same way water is always subject to gravity. It moves toward the lowest point available to it. In a well-designed filter, that path downward is not open and direct. It is tortuous. The water has to navigate through the spaces between particles of gravel and sand, following a winding path that brings it into contact with an enormous surface area of filtering material. A single cup of sand contains billions of individual grains, and the total surface area of those grains, if you could unfold and flatten all the microscopic irregularities of each grain's surface, would be measured in square meters, not square centimeters. As water moves through that maze of surfaces, particles suspended in the water collide with the grain surfaces and stick. This is not filtration in the simple sense of a screen blocking objects larger than its holes. It is a much more complex process of collision, adhesion, and adsorption operating simultaneously across an almost incomprehensible number of contact points. The gravel layer at the top of the filter does the coarsest work. It catches leaves, insects, large debris, and visible sediment. Without this layer, the finer materials below would clog rapidly and the system would stop functioning. Think of gravel as the first line of defense, not removing what is most dangerous, but removing what is most physically obstructive so the more delicate work can happen below. The coarse sand layer below the gravel continues the particle removal process at a finer scale. Water that looked clear after passing through gravel often still contains significant suspended turbidity, fine clay particles and organic material that give water a cloudy or brownish appearance. Coarse sand reduces that turbidity substantially. The fine sand layer below that is where the most significant microbial reduction occurs in a well-operated biological filter. Over time, as a filter is used regularly, a community of microorganisms establishes itself in the top few centimeters of the fine sand layer. This biological layer, sometimes called the Schmutzdecke, which is a German word meaning dirty layer, is paradoxically one of the most important filtration components in a slow sand filter. The organisms living in this layer are not pathogenic. They are predatory toward pathogens. They consume bacteria and other microorganisms that pass through the gravel and upper sand layers, dramatically improving the biological safety of the filtered water. A new filter does not have this layer. It takes weeks of operation to establish. But once established, it transforms the filter from a purely physical system into a biological one as well. The charcoal layer performs a fundamentally different kind of work. Charcoal, and particularly activated charcoal, which has been processed to increase its porosity, has a surface structure that is extraordinarily effective at adsorption, meaning the adhesion of dissolved molecules to a solid surface. When water carrying dissolved organic compounds, certain pesticides, chlorine, and chemicals that produce unpleasant taste and odor passes through charcoal, those dissolved substances adhere to the carbon surface and are removed from the water. This is why filtered water often tastes dramatically better than the source water, even when the source water is technically safe to drink. Charcoal cannot remove dissolved minerals or heavy metals effectively without being specifically activated and optimized for those contaminants, and it cannot remove viruses reliably. But for organic chemical contamination, taste and odor problems, and general improvement of water quality, charcoal is one of the most effective natural filtration materials ever identified. The cloth or fine mesh at the very bottom of the filter serves as a final physical barrier that prevents the filter materials from escaping with the water. It is also the checkpoint for particle size, catching anything that has made it through the layers above without being trapped. In a well-built filter, very little reaches the cloth layer, which means the cloth remains functional for a long time before needing replacement. Building a working version of the system requires a container large enough to hold the layers with sufficient depth to be effective. Typically, at least 30 centimeters of layered material is recommended, and a way to exit filtered water from the bottom. A plastic bucket with a small hole drilled near the base, fitted with a short tube or spigot, works well. So does a large plastic bottle with the bottom cut off and the neck pointing downward, nested inside a collecting container. The specific container matters less than the depth of the layered materials and the order in which they are arranged. From bottom to top, the sequence is cloth or fine mesh, then charcoal in a layer approximately 5 to 8 centimeters deep, then fine sand in a layer approximately 10 centimeters deep, then coarse sand in a layer approximately 8 centimeters deep, then gravel in a layer approximately 8 centimeters deep. Above the gravel, pour the water to be filtered slowly and allow it to percolate through without disturbing the layers beneath. The charcoal used does not need to be purchased. It can be produced from wood or agricultural waste through a process called pyrolysis, which is essentially burning organic material in a low oxygen environment so that it chars rather than combusting completely. The same fire that a rural household uses for cooking can produce usable charcoal from wood or coconut shells or corn cobs or bamboo. That charcoal, broken into small pieces and rinsed before use, is an effective filtration material. This matters enormously for accessibility. In communities where purchasing activated charcoal from a commercial supplier is not practical or affordable, locally produced biochar from available materials provides the same basic function. The filter can be built from entirely locally sourced materials in virtually any environment on Earth. The sand used should ideally be clean, meaning free of clay and organic material before use. River sand, washed thoroughly with clean water to remove fine particles and organic matter, is excellent. Sea sand contains salt and should be thoroughly freshwater rinsed before use. Gravel from a stream bed, washed clean, is ideal for the top layer. In settings where sand and gravel are not naturally available, crushed rock and similarly sized inorganic materials can substitute. The biological and chemical requirements of the filter are not strict about specific mineral composition. Almost any inorganic particulate material of the right size range will provide the physical filtration function. The water that comes out of a well-built and properly operated gravity filter is significantly cleaner than the water that went in. Studies conducted on slow sand filtration systems, including simple household scale versions, consistently show reductions of turbidity by more than 90%, reductions of bacterial contamination by more than 99% in well-established filters with mature biological layers, and significant reductions in organic chemical contamination. This is not anecdotal. It is documented in peer-reviewed public health literature from research conducted across multiple continents. The World Health Organization recognizes slow sand filtration as an appropriate technology for household water treatment in resource-limited settings. This is not a fringe or alternative approach. It is mainstream public health practice, validated by decades of research and field experience. However, it is essential to be honest about what the filter does not do, because the lives of people who depend on it may rest on understanding the limitations clearly. A gravity sand filter does not reliably remove viruses. Viruses are far smaller than bacteria and are not effectively trapped by sand filtration alone. In settings where viral contamination of water sources is a concern, filtered water should still be treated by boiling, solar disinfection, or chemical treatment with chlorine before drinking. The filter also does not remove dissolved heavy metals like arsenic or lead, which are serious concerns in some geological settings and industrial areas. And a filter that is not maintained, meaning one that becomes clogged, one whose biological layer is disturbed or dried out, one whose charcoal layer is never replaced, one that is contaminated after filtration, can fail to provide the protection it is capable of delivering. The filter is a tool, like any tool, it must be used correctly and maintained appropriately to perform reliably. That said, in the context of the actual water crises that affect the most people, the limitations of the gravity filter are often not the relevant constraints. The leading causes of waterborne illness and death in most affected communities are bacterial, protozoan, and suspended sediment contamination, all of which a properly built and operated gravity filter addresses effectively. In the global burden of waterborne disease, the conditions most prevalent in the communities, where simple filtration could have the greatest impact, are also the conditions most amenable to what simple filtration can provide. The match between the tool and the need is real and documented. There are also complementary approaches that can be combined with gravity filtration to address the limitations. Solar disinfection, or SODIS, involves filling a clear plastic bottle with filtered water and leaving it in direct sunlight for 6 hours or more. Ultraviolet radiation from sunlight damages the DNA of pathogens, including viruses, rendering them unable to reproduce and cause illness. When filtered water, which has low turbidity and therefore allows sunlight to penetrate effectively, is treated with SODIS after filtration, the combination addresses both bacterial and viral contamination, using only sunlight in a clear plastic bottle. The combination of gravity filtration followed by solar disinfection costs nothing beyond the initial construction of the filter and is effective against the full spectrum of biological water contamination in most field settings. This two-step approach has been validated in extensive field studies and is recommended by the WHO as a household water treatment strategy for resource-limited settings. The history of centralized water systems and bottled water markets needs to be examined honestly, not because those systems are malicious, but because understanding how they became dominant illuminates why simpler alternatives became invisible. Municipal water treatment was a genuine triumph of public health engineering. The introduction of filtration and chlorination to urban water supplies in the late 19th and early 20th centuries produced dramatic reductions in waterborne disease mortality in every city that adopted them. These were not marginal improvements. Cholera, typhoid, and dysentery declined by orders of magnitude within years of water treatment implementation. Clean, centralized water supply is one of the most significant contributors to the increase in life expectancy over the 20th century. It deserves the credit it receives, but centralized systems only work where the infrastructure exists. And infrastructure takes decades and billions of dollars to build. In the interim, and in the many places where that interim has stretched into generations, people have needed something else. The something else has too often been bottled water, a product that costs hundreds of times more per liter than municipal water, that generates an environmental catastrophe of plastic waste, that is not reliably safer than local tap water in many settings. And that has become a multi-hundred-billion-dollar industry precisely because it monetizes a need that gravity filtration could address for free. The bottled water industry has a strong incentive to maintain consumer belief that safe water can only come from a commercially produced source. That incentive shapes marketing, shapes policy advocacy, and shapes the visibility of alternatives. A bucket of sand and charcoal that produces safer drinking water than most bottled water brands costs $2 once and then works indefinitely. It does not appear in advertising, it does not have a distribution network, it does not generate shareholder returns, and so it remains unknown to most of the people who could benefit most from it. Think about what it means to live in a community where children are dying from water that looks clean, where adults spend hours every day managing water collection and storage and hoping it is safe enough. Where the solution has existed for thousands of years, is validated by modern science, can be built in an afternoon from materials available within walking distance, and costs less than a single bottle of commercially filtered water. The gap between what exists and what is known is not a gap in the technology. It is a gap in the transmission of knowledge. And closing that gap, village by village, school by school, community organization by community organization, is the actual work of addressing the water crisis at the scale where it matters most. Rain still falls on every continent. Gravity still pulls water downward through every substance it encounters. Sand still traps particles. Charcoal still absorbs contaminants. The biological communities that colonize a sand filter and consume pathogens still establish themselves wherever the conditions allow. None of that physics has changed. None of that chemistry has changed. The natural processes that ancient civilizations observed and harnessed and documented have been operating continuously without interruption, since before the first human being thought to place a layer of gravel over a layer of sand and pour water through it. The knowledge is not lost. It is documented in medical texts and engineering journals and public health literature and historical records, spanning 3,000 years of human civilization. It is taught in environmental engineering programs at universities. It is practiced in field settings by humanitarian organizations, working in disaster zones and refugee camps and underserved communities around the world. It exists. What is needed is not invention. What is needed is transmission. The movement of knowledge from the places where it is held to the places where it is needed. That movement does not require technology more sophisticated than a conversation, a demonstration, a video, a single afternoon spent showing someone how to layer gravel and sand and charcoal in a bucket, and why each layer is doing something irreplaceable. The rain still falls, the earth still filters, gravity still works without being asked. And the distance between a child dying from contaminated water and a child drinking water clean enough to be safe is sometimes no more than the knowledge of how to build a system that costs $2 and takes an hour to assemble. That knowledge exists. It has always existed. The only question that remains is who will carry it to the people who need it.